Let's look at a couple of very simple examples using psychrometric charts. So in this case, I've got a mass of air, and I'll say 10 kilograms of air. It's at 45 degrees C, 1 atmosphere, so the psychrometric chart is applicable. And I have 10% relative humidity. It's cooled at a constant pressure to 15 degrees C. And what I want to know is, does condensation occur? If it does, then how much water vapor condenses, and if not, figure out what the relative humidity is at this given state. So I can use the psychrometric chart. So let's come down and find this point. It's 45 degrees C, 10% relative humidity. Okay, so let me zoom in slightly. Well, not that much. Okay, 45 degrees C and 10% relative humidity. So right on this point right here. If I cool it at constant pressure, then it's going to stay right on this constant humidity line. In other words, the amount of air and water in the curve will not vary. And so it comes over to this point, right over here on the same humidity line, okay, until it's at 15 degrees C. Now at this point, I'm going to stop the problem, right? It has not reached the saturation curve, this top edge, so therefore nothing will condense. But the relative humidity has changed because at this temperature the vapor pressure has decreased. And so the relative humidity that they have asked for here is between 50 and 60, so maybe 53%, 54%. It's a little bit up to your eyes, but no condensation happens, and I can find the relative humidity at the final given state. So let's work a variation on this problem. Okay, I'm going to do this now with 40% relative humidity. So it's a minor change, right? But still 45 degrees C. So my initial point is right here. Okay, that's 45 degrees. It's marked here. 45 degrees up to, well, I did 30%. I meant 30%. That's what I did. So we'll go with that. Then I'm going to cool it at constant humidity because the mass of the vapor and the air will not change just because I'm cooling it until I reach the saturation curve. So at this point, the temperature is 23.5 degrees. I haven't gotten all the way down to 15, but I start with the condensing water. And now then, it's going to stay condensed, but water is going to be dropping out as I continue to cool. So I go straight across until I reach saturation. And then as the water vapor drops out, I drop down along this curve until I get 15 degrees. Now the humidity has changed. It's now down to this lower value. So whereas I was at approximately 0.0184 kilograms of water per kilogram of dry air, now I am at approximately 0.018 kilograms of water per kilogram of dry air. I can use that to calculate the mass of water that condenses. So first I have my values I read from the tables. The difference between those will tell me how much water condenses per kilogram of bone dry air. Okay? Now, the problem is I need to figure out how much water I actually have. So that means I need to figure out, for 10 kilograms of moist air, how much dry air do I have? So I just need to play some little games with the masses. I started by saying, let's take 1 kilogram of dry air. At the beginning, that was 0.0184 kilograms of water per kilogram of dry air. So that means for 1 kilogram of dry air, I would have 0.0184 kilograms of water, or 1.0184 kilograms of moist air. All right? So the mass of dry air per mass of moist air is 0.98, 1 divided by this. So now I can use that to convert from 10 kilograms of moist air to get how many kilograms of dry air. That can be multiplied by my delta W to determine the mass of water that actually condenses. And in this case, 10 times 0.98 times this delta omega gives me 0.17 kilograms of water will condense from 10 kilograms of dry air. That concludes our lessons on reading the psychrometric charts.